All right, before we move on, I thought now is the perfect time to discuss this topic, holonomic versus non-holonomic basis systems. And it's just because we're talking about the commutator, and the commutator fits in with this topic really perfectly. So we have to understand what we're talking about when we talk about a basis system for our underlying spacetime. And for the purposes of this, I'll talk about a two-dimensional manifold. So we're dealing with just two coordinates, say x0 and x1. And once we have this coordinate system, which we know we can always have, well, heck, let's just go with the full 4 dimensions. What difference does it make right now with this example? But every point in space-time, of course, can be given coordinates. And we know that because it is a fundamental presumption of the theory that space-time is modeled by a 4-dimensional manifold. And there, by definition, a 4-dimensional manifold can have coordinates. So in this coordinate system, we know that we've already found that, or explained and talked about at great length, that each point in the space-time is given its own vector space V. And the coordinate basis system for that vector space V are these partial derivatives, these operators, these partial derivative operators, these differential operators that establish the basis system. So the basis is 0, partial 1, partial 2, partial 3, often written partial mu, and of course what this actually means is d by dx0, d by dx1, etc. Right? That's what that all means. And every tangent space has its own basis system. And these spaces, as we've talked about many times, are not are totally independent one of each other. The only conceivable way of talking about this space having a connection with this space is through the actual connection, right? And so if the space-time has a connection, that's a way of linking these things together. But that's not part of our conversation right now. Right now we're talking about these basis systems. So this kind of basis system is called a coordinate basis system. It's also a holonomic basis system. Any basis system that's attached to a coordinate system is holonomic. And if we did a change of basis, if we took this basis system and changed it to another one, this blue one, for example, which I call the prime system, and I like to put the primes on the index itself, right? So the x0 prime system, the x1 prime system. Other ways of doing it that you'll see a lot is like, say, x hat 0. I don't like that. I much, this is absolutely my favorite. The only weakness of this is that you've got a superscript of a superscript, right? That's a little annoying. But, LaTeX can handle it pretty well. So when you're doing publishing and writing, everything is fine. Anyway, the blue system would be the prime system. And if you transform to this system, what you're really kind of saying is that if you have a function on the space-time, f of x, where x is a point in space-time, I can write that function, it's a function on the space-time. It's really dependent on the point in space-time. But I can write that as a function of x0, x1, x2, and x3, or I can write it as a function of x0 prime, x1 prime, x2 prime, or x3 prime. I just do a coordinate transformation between these two coordinate systems. I presume that I know x1 prime as a function of x0, x1, x2, and x3. Likewise for all the others, or say x0 prime. I guess the way I should write that down is I know x mu as the muth function of, wait a minute. I know x mu prime as a function of x mu. X mu prime is a function of, say, x mu, where this represents all four. So I know these transformation functions and their inverses. Like I also know x mu as a function of x mu prime, right? I know all of that stuff. Anyway, with those functions, with those transformation functions that I just erased, you can take any function on the spacetime and turn it into a function of the new coordinates or the old coordinates. But once you're dealing with this, but the basis vectors for the old coordinates are going to be partial alpha, and for the new coordinates will be partial alpha primes. And the partial alpha primes will be easy to take derivatives of those functions, and the partial alphas will be easy to take derivative of those functions. And as you transform coordinate systems, you basically change your basis. Let's work a quick example of this in two simple dimensions, just so you can see how trivial this really is. Here I've written down a very straightforward, we're going to use 2 dimensions, and we have a polar system over here, r and theta, and the Cartesian system here. And we know x as a function of the polar coordinates, and y as a function of the polar coordinates, and we know the radial component, the radial coordinate, as a function of x and y, and the, I guess we'll call that the azimuthal coordinate. Well, I guess not. We'll call it the polar angle as a function of x and y. Now, if we were to write this in the notation of our last section, x would be unprimed 1, y would be unprimed 2, r would be prime 1, and phi would be prime 2, and you get this object. But this is obviously totally the same thing, right? It's the unprimed and the prime system. The unprimed system is x, the prime system is r. So these are the coordinate functions that you might, over here we would write x mu is a function of x mu prime. And over here we would write x mu prime. They're all functions of x mu, like that. Then the basis set for any vector space at any point will just be the differential operators xy in the unprimed system. The differential operators are theta in the are phi in the prime system, and we would add put the prime there on the differential operator. And then any function we have that's a function on the spacetime, it'll either be a function of x1 and x2 or x1 prime and x2 prime. If it comes as a function of x1 and x2, then everywhere you see an x, you just substitute r cosine theta. Wherever you see an x2, you substitute r sine theta. You see, everywhere you see an x1, you would substitute this. Wherever you see an x2, you substitute this. And then all of a sudden you have a function of the polar angles. And likewise, you can go backwards using these two functions here. Everywhere you see an r, you substitute square root x squared plus y squared. Everywhere you see a theta, you substitute inverse tangent x over y. So that's pretty easy stuff to handle. But what's important to see is that this is a basis system of a point in spacetime. So we have this point in spacetime. I'll just sort of indicate it one way or another out on this, floating out on the spacetime. And it has its basis system phi mu. We'll say we're in the unprimed system. Now, phi mu prime is a basis vector at this point, regardless of what system you're in, right? I usually do it this way. Sorry. Regardless of what system you're in, phi mu prime is still a basis vector at this point, and it is a member of the vector space. It's just a different derivative with respect to a different coordinate system. So you should always be able to express this vector in terms of this basis. And likewise, you should always, if you were in the prime coordinate system, this would be the coordinate basis, and this would be sort of a different, a foreign basis. But again, this basis vector must be expressible in terms of that basis system. They're both basis systems, regardless of your coordinate system. And this is an important point. This is still a basis, and they're both bases. Just one is the coordinate basis because it's actually sympathetic to the particular coordinate system that's out there. The other one is sympathetic to some other coordinate system, not the one that's out there. So, but it's still a potential basis because they're two linearly independent vectors in this case, a two-dimensional vector space. So you should be able to write any other vector in terms of these guys or these guys. It's just that now with the prime coordinate system, this is our natural coordinate basis. So the question is how do we write this in terms of this or this in terms of this? Well, let's imagine that we have we do have a function that's a function of x and y. So that would be a function in the unprimed basis. And we take a differential operator in the prime basis and we act on that function. Well, through the chain rule, it just pulls out that we get the function with respect to the first variable multiplied by the partial of the first variable with respect to the variable whose derivative is operating here. And likewise, it's the function with respect to the second variable multiplied by the second variable's relationship to the function that's in question. This is just the chain rule, and then of course you just have to remember that fx is by definition df dx, right? That's no longer, I'm no longer really using this as a subscript. This is now just indicating it's a derivative. That might not be appropriate. I'm just trying to decide if I've ever seen this notation. This is certainly what I mean, right? There's no doubt this is what I mean. But every time I see this with the bar, I always see an index here. So I think I've just accidentally created some notation. I think what I really want to just say is straight up that. But, you know, in a lot of math books, no, that's not true. Because in a lot of math books, they will do that indicating without the line. So I just have the line there. So this is fine. I've seen this notation is always is completely ubiquitous in the study of partial differential equations. That's the partial derivative of f with respect to x. The only difference is we've got this line here. The reason the line is not too relevant is the only reason you would have a single line is to distinguish it from a double line, which is the covariant derivative. But this is pure math we're talking about. There's no covariant derivatives really in sight. So you wouldn't lose, there's no possibility for confusion. I'll just leave the line though. I'm okay with it. All right, so continuing on, we are now looking at, so we have this expression here. And this we can completely calculate because we know the prime coordinate system, which is the r theta coordinate system, the way we've done our notation. And the unprimed, we know the relationship between the prime and the unprimed coordinate system. That is, we know x as a function of r. We know x of r and theta, so we certainly can figure out dx, dr, right, without any trouble. Likewise for this as well. So we just go back to here and we look at these two expressions. The partial of x with respect to r is simply cosine theta. The partial of y with respect to r is simply sine theta. And kaboom, we have our expression. Now what's missing in this expression is an f here and an f here, which is what that is and what that is. But the reason those are missing is because I can just pull it out here, right, and put it over here like this. So I now have the derivative with respect to the primed coordinate r in terms of a differential operator of the unprimed system, right, and acting on f. So this operator here is entirely equivalent to this operator here. Now this operator here is clearly a function on the space-time, right? It really depends where you are. If this is the space-time and that's r and that's phi, right, at that point. At that point, I have to take the value of phi, right? That point is a coordinate r phi. I take that value of phi, I take its cosine, I take its cosine, right? And then I multiply that cosine by the operator x, and I operate it on f. So I take the function f, operate it on, operate against it with the differential operator partial x, multiply by cosine phi, and that will end up being another function, right? Because remember, f is a function of f and y, x and y, so this differential operator is going to return another function of x and y, and I evaluate that at this point. I evaluate that at that point, and so that's not a problem. Now, of course, I have to figure out r theta. Remember, if this coordinate system I'm using is the xy coordinate system, I have to figure out the r theta value at that point. But again, we can do that because we know these two expressions here, because we know all of the coordinate transformations in both directions. So it's perfectly acceptable to get rid of this f and just say that this operator here is equal to this operator here, which is a way of saying that this vector is the basis in our coordinate system, our xy coordinate system. The partial x and partial y are our coordinate basis vectors. So this vector is just a linear combination of those coordinate basis vectors. We can do the same analysis for the second unprime, or the second prime coordinate, phi, and you come up with this expression here. Now you're taking dx d phi and dy d phi, which in our example would be r minus r sine theta for dx d phi, or partial x partial phi. Partial y partial phi will be cosine phi r, right, which is what these two are. And likewise, we could do it backwards. We just have to, we have to assume that our function on the space-time is set up to take the r phi variables. And if we operate it with this, with the unprime basis differential operator, or the unprime differential operator, we have to break up the chain rule in this fashion. But this is just the same process. We know r as a function. We know r as a function of x and y, and we know phi as a function of x and y. And so these derivatives can be taken very easily, and in fact I did it here. They're a little more complicated than the other ones, right? This is just an algebraic expression. This ends up being the derivative, let's see, this is phi is the inverse tangent of x over y. So you have to know how to take the derivative of the inverse tangent, which if you remember is 1 plus x over y squared, right? Inverse tangent of theta is, the derivative of that with respect to theta is 1 plus theta squared. I guess theta is a bad variable to use. Try to say z. Z is 1 plus z squared. So in this case, z is x over y. So that derivative is going to be 1 plus x over y times the derivative of x over y, which is going to be, let's see, this was the derivative with respect to x, so it's going to be 1 over y. So, and that's what that is. That's the 1 over y up there. That comes from the chain rule. But anyway, what you have to do here, of course, is you have to recognize that the x squared plus y squared equals r squared. So you have x over the square root of r squared, so you have x over r, that's the cosine of phi. You have to recognize that x over r is the cosine of phi. You want this whole side here to be in terms of the coordinates of the coordinate system that you're using. This is the prime coordinate, but right now we're imagining ourselves this is the unprime coordinate, so we're imagining ourselves in the prime system. So everything over here needs to be part of the prime system, and this has to be the unprime system. In other words, you don't want any x's and y's on this. You want this all this side in terms of phi and r. But anyway, this ends up being y squared plus x squared, which is r squared. So you have y over r. You have 1 over y over r squared. Wait, something's wrong. Yeah. Obviously, look what I've got here. I've got dr dx, d phi dx. D phi dx is going to be 1 plus x over y squared. Then you have to multiply by the derivative of this with respect to x, which is 1 over y. Oh, yeah. Then you multiply. Then what you have to do is you multiply the top and bottom by y squared to get y squared plus x squared. Then you end up with y on the top, right? And that's y over r. Y over one of the r factors, because the bottom is now r squared. So y over one of those r squareds gives you cosine phi. And then you have a 1 over r remaining, and that's what this guy is. And the negative sign comes. Oh no, the negative sign is for the other case, dy. But if you do this again, you end up. If you do this, if you solve this, but you have a y here and a y here and a y here, you end up with this expression, which is obviously very similar. But the point is you have the unprime basis vectors now in terms of the prime basis. So if you have some function on the space-time, f of x and y, and you want to know what phi r is on it, you have two choices. You can go in there and convert this and that into phi and r, so you end up having, you convert this into a function of r and phi, and then the derivative is easy to take. Or you say, okay, well, this is the same as this, so I'll just take the derivatives with respect to x and y and multiply by cosine and sine theta appropriately, and that'll be the same answer. All right, so let's take a close look now at what we've done and why it's important. So now we know that these vectors that live inside the vector space V at some point in space-time, right? Every point in space-time has a little vector space. So these two vectors, partial r and partial phi, they're differential operators that can act on functions of the space-time, so they must be part of this vector space, because this vector space contains all the first-order linear differential operators, and these are first-order linear differential operators. And we have expressed them in terms of the coordinate basis at the point P. So we're kind of, we're at this point assuming that our coordinate system here is the x, y coordinate system. Now, another thing about a vector space is it has an inner product. We get to choose what that inner product is if we're speaking in the world of mathematics. In the world of physics, of course, nature chooses the inner product, is what I've been saying. But in the world of mathematics, we get to choose this inner product. And so we put vectors into the inner product, and we have to define how that inner product works. For the Cartesian space we're dealing with, we're going to presume that the inner product works the following way. Partial x equals 1, partial y equals 1, partial x, partial y equals 0. In other words, we're going to deal with something that is orthonormal. Right, this is an orthonormal basis system. This is the orthonormal inner product. So remember, we picked this, right? We've chosen this. I didn't have to be this way, but I'm going to choose a nice and easy inner product where these basis vectors are orthonormal. So the question is all right, so I've got these two basis vectors for this prime system, where if I change the coordinates, to r and phi, right, then in that coordinate system, I have these guys are my coordinate basis. But since this coordinate basis is clearly written in terms of the other system's coordinate basis, this inner product, once I define it on one coordinate system will flow into the other coordinate system. And I can do a very straightforward calculation to show that. I can show partial r, right, is going to simply be the substitution for r and r of this expression. And this is all linear. It shows you how important being linear is, right? This is completely linear, so I just blow this up, and you don't even have to write this out, right? This term is going to combine with this term to give me a cosine squared inner product x with itself, which we know is 1. So I get a cosine squared. Remember, this is going to be a real number, right? That's the whole point. The inner product takes two vectors and gives you a real number. So the first part of this real number is cosine squared. Then I have cosine squared times cosine of phi times sine of phi. But the inner product is partial x, partial y, which is 0. So that term goes away. Then likewise, I get sine cosine of sine phi, cosine phi, but I have y x, so that goes away. Then I have sine squared y, which is 1. So I have cosine squared plus sine squared, so I get 1. So this orthonormality, so these two guys, phi r is phi r is normal. So I have to check. Phi r, partial r, as a vector with its inherited inner product in the new coordinate system is going to be normal. So I want to check now the other one. I want to check partial phi, partial phi. And if you do that, the problem is if you can look at it, you can see you've got sine and cosine. Everything's going to work out exactly the same way. You'll get this minus sign involved, but the problem is that it's not equal to 1, right? Because you can pull out everywhere where I pulled out cosine and sine and cosine, I'm going to pull out an r or a minus r as well. And what that's going to end up with is giving me an r squared left. Everything else will go to 1, but I'll be left with with an r squared. Right? You can almost see that, right? This guy is going to combine with another. I'm going to put this in the left-hand slot and this in the right-hand slot. So the only things that are survived is minus r sine phi times itself, which is just r squared sine squared phi, and r squared cosine squared phi will survive. So you end up with r squared times sine squared phi plus cosine squared phi, which is 1, so you end up with r squared. So this guy here is not normal. And then you can see that the inner product for partial r, partial phi, that will actually be 0. If you work it all out, it'll all cancel to 0. So it's ortho. These two vectors here are orthogonal, but they're not orthonormal. So we kind of like orthonormal. So let's say we wanted an orthonormal basis system. Now what would we do? Well, the troublesome part here is this r, right? So if I multiplied this basis vector by 1 over r, I'd be okay. So what does that actually mean that we're doing? Well, we imagine that, we have our coordinate system out here. And at this point, we have its vector space, and we're now in the R phi system. So the coordinate vectors are, the coordinate basis is partial r and partial phi. Well, what I'm now going to do is I'm going to say, no, I'm going to change to new basis vectors. I'm going to call it ER. I'm going to leave that as partial r. So it's going to be partial r plus 0 times partial phi, right? It's a vector field. It's just got none of this component. It's trivially related to the coordinate vector field. But then I'm going to create E phi, which is going to be 1 over r partial phi. So this leading factor changes depending on what point you're on, because it depends on the coordinate r. So this guy is definitely not the coordinate basis vector because it's not simply partial phi. But what is nice is if I choose these two guys as my basis vector for this space, what I've done is I'm sticking in the R phi coordinate system. I'm still in the R phi coordinate system. I haven't changed coordinate systems, but I'm now changing basis vectors by introducing that factor of 1 over R. And that's totally fine because these two guys are linearly independent. And the vector space that I'm dealing with in this case is only two-dimensional, right, for this example. But if I have two linearly independent vectors, that can be a basis. But what's really nice is that in this particular system, ER, that still equals 1, right, because I haven't changed that at all, right, that's 0. E phi now actually equals 1, and ER, E phi equals 0. So these two guys are in fact orthonormal. So I've created an orthonormal basis system by just introducing this factor of 1 over R. So that's great. Now I can do that at every point in space-time. I now have a vector space installed where I'm now dealing with ER and E phi, which I know is 1 over R times the coordinate basis partial R. Now notice I still always refer to the coordinate basis when I do this, right? I still refer to it. And if I ever were to operate on a function using these differential operators, which we do from time to time, I would still put that function in terms of, I would want to see that function in terms of R and phi so I can quickly apply these operators. I would substitute, if I had a vector, say I had a vector in this vector space, I called it x, and x was, say, 7ER plus 4E phi. Well, and then I had some function of R and phi. Well, if I were to apply x onto the function, I would apply 7 partial R plus 4 over R partial phi. And at this particular point, P, I would evaluate it at the point P. Well, P has a coordinate, R and phi of the point P. So I would evaluate this at the point P, which would give me a value of R there. I'd calculate that number, and then I would apply the whole thing to the function f, and I'd get an answer, and that answer would be a number. So it's not really a big change. All I've done is added this factor. But now I can ask a pretty important question. The question I can ask is, well, wait a minute. Why go through this mess I just showed you? Why have to take these basis vectors, transport them back into the coordinate basis system, operate on functions that way? Wouldn't it be nice if I could just do a coordinate transformation from the prime system, R phi, into, say, a double prime system, which I would call rho, let's do it in blue. I'd call it rho theta, right? So there's some other coordinate system out there. And that coordinate system is rho theta. Let me clean this up. Okay, that's much cleaner, right? So I was in an R phi, and now I want to go to some other system, R theta, or rho theta. And what I want is, if I'm really going to stick with ER and E phi as my basis vectors, wouldn't it be nice if ER simply equaled partial rho and E phi simply equaled partial theta? If I could find such a basis system, then my new orthonormal basis would just be the coordinate basis of some other new coordinate system. So I would need rho as a function of phi. Rho as a function of R and phi. I would need theta as a function of r and phi, and likewise I would need r as a function of rho and theta, and I would need phi as a function of rho and theta, right? I need a coordinate transformation. That's what this is. This here is a coordinate transformation. I need a coordinate transformation from the prime system, that is the r theta system, to the double prime system, which would be rho and theta. But I have to pick rho and theta correctly so that this guy here, so our new orthonormal system is just the straight up coordinate basis of this new coordinate system. Because remember, I never changed coordinate systems when I created this basis. I stayed in the coordinate system and I just sort of added this factor into the basis. Well, so what I just described, the process that I just described of finding a new coordinate system that absorbs this basis, you can't always do it. You just can't always do it. In fact, you rarely can do it. But when you can do it, that would mean that this basis was holonomic, because there is a coordinate system out there that absorbs this basis as its coordinate basis. When you can't do it, that's when you have a non-holonomic basis system. And there are plenty of non-holonomic basis systems out there, and we will use many, I'm sure, eventually. But the reason we're talking about this now is because the way you determine if a basis system is holonomic or not is very simple. The short answer is you take ER, the commutator of ER and E phi, and you ask, is it equal to 0? Now, this is only 2 dimensions, so there's only one commutator to check. If it was in multiple dimensions, you would take E mu, E nu, and ask, is it equal to 0? And this is so this leads to every possible pair, right? So in a 4-dimensional space, you'd be E0, E1 equals E0, E2 equals E0, E3 equals E1, E2 equals E1, E3 equals E2, E3, and they all have to equal 0. If they all equal 0, then there is indeed some coordinate system out there whose coordinate basis is equal to this particular basis E, whatever basis you choose. Now, why is this the case? What is the logic behind all this? Well, you may remember we had this, what we learned about the commutator is that it tells you how these mismatched points in curved spacetime, if you proceed a parameter distance delta sigma, delta lambda along these curves, delta sigma, delta lambda. And I can get to this point by moving delta sigma this way and delta lambda that way. And I can get to this point by moving delta lambda this way and delta lambda that way. If these lines, if these curves were the coordinate curves of a coordinate system, and this was the circumstance, it just wouldn't work. Because if this was the origin of the system, if that was the origin, then the coordinates of this point would be delta sigma, delta lambda, and the coordinates of that point would be delta sigma, delta lambda. It'd be the same coordinates, right? Both of these points would have the same coordinates, and there would be ambiguity. Your coordinate system would have a fundamental ambiguity into it. So the distance between these two has got to be 0. Another way of looking at that is a function on the spacetime evaluated at this point and this point. If it's different, then they're 2 different points, and that's no good. Arbitrary functions on the spacetime. Arbitrary functions on the spacetime. Because you can imagine that there's some function on the spacetime that happens to give that point and that point the same value. That doesn't make it good. it's got to be an arbitrary function in the space-time. Any function, every function, going through this exercise, calculating the values, just like we did in the last lecture. So the way that happens is, remember that, so the vector field that gave, so the vector field that's always tangent to these curves, that is the basis vector field, right? That is, if this is the coordinate curve, right? If this is the coordinate curve in space-time, its basis vectors, say this is the x0 coordinate curve, its basis vectors are partial 0. If this is the x1 coordinate curve, its basis vectors are partial 1, right? So in order for this point and this point to always coincide, we've already shown that partial 0, partial 1, right? The two vector fields, they must commute. This because this difference is given by the commutator, right? We went through that exercise in our last lecture. These are vector fields, right? This is like vector field x, vector field y, right? Equals 0. In that case, I had a vector field x here and a vector field y here. Well, now that vector field, the curve is the coordinate curve, right? The coordinate curve, which is, and the tangent vector of the coordinate curve is just the basis vector. So you just put in that substitution, and now you can see why, using the analysis we did for the last lecture, and you can even use the flat space-time analysis, that is fine too. That commutator has to be 0 in order for this to be a legitimate coordinate system. So if you're given, so now if you're given a basis, so in a legitimate coordinate system, like if this is a coordinate curve, and this is a coordinate curve, and this is a coordinate curve, and this is a coordinate curve, then these points will in fact be just one point, right? This would work. However, that's not what we're dealing with. We're saying, okay, I've got ER and E phi, right? Those are the tangents. That's the basis I'm using. So there's some curves in space that follow those tangent vectors. And those curves in space that follow those tangent vectors will always have this mismatch problem. And therefore, there is no coordinate system that can just be shifted to that will make this and this equal to phi r and phi, well, I guess we did phi rho and phi theta. Anyway, so that's the point I wanted to get at. I wanted to attack that question, and the reason was we just gone through this whole thing with the commutator, and I just wanted to show you how a non-holonomic basis actually exploits this issue, showing that if you have a proposed basis vector field, in this case E phi and ER, which was given by this expression here, this 1 over r partial phi and partial r. The question is there a coordinate system where these will be just coordinate bases, simple, easy coordinate bases? And the answer is no. Well, actually, we didn't check that. But what I want to check is I want to check partial r, commutator 1 over r partial phi. And the way this expands is this commutator becomes this partial r, the first one acting on the second, and minus the second acting on the first, which is what this is. We always presume that there's some test function out here, right? So we have some test function out here. I guess likewise I should put it here. And if we expand this, we take the partial r against 1 over r, get minus 1 over r squared partial phi, and then we're left with 1 over r partial phi, and then this is minus 1 over r partial phi partial r. But these two commute, right? Partial derivatives commute. So these two cancel. I guess I better cancel them in blue. So those two cancel, but what's left over is not equal to 0, right? It's not equal to 0. So these two don't commute, therefore they are not a coordinate. There is no coordinate system that you can shift to express these two guys in terms of purely the coordinate basis. Okay, so that was a little side diversion. This concept of holonomic and non-holonomic basis, it becomes important when we deal with, when we move along and we talk about the tetrad formalism of general relativity, which is a very interesting, fun formalism where all basis vectors are basically replaced by vector fields. You never use the coordinate basis in the tetrad system. You always use 4 linearly independent vector fields, and they're inevitably not inevitably, they're often non-holonomic. Okay, we'll back on track towards curvature next time.